Sure, here we go. Good. So yeah, tonight's the night, right? You guys are all going to show up for that. We have 3 rooms for the test. You all got an email about where the rooms are. It's VLSB this time instead of Gmail. If you did not get the email, then let me know, and I'll tell you where you're going. We're doing it by section number instead of last name first letter, so make sure you go to the right room. So today, there's a few more things I want to cover with oscillations to the beginning of waves, but I want to make sure everybody's got their last minute questions answered for the exam. Are there any questions people have about the exam? Yeah. Yeah, right. Right. So the question is about center of mass and velocity of center of mass, and it's and the question in particular you're asking about is bumper cars. Is that right? So in that problem, okay, so first of all, when two of those bumper cars collide, is it elastic or inelastic? It's elastic. So what's conserved? So energy is always conserved, but what kind of energy is conserved? Kinetic energy is conserved, absolutely, and also momentum is conserved. If it were inelastic, what would be conserved? Just momentum. That's right, and energy, but that may not be useful for us because kinetic energy won't be conserved. But anyway, that's right. So we know that both kinetic energy and momentum are conserved. If momentum is conserved in some system, so let's get the system, and you have a choice in these problems, right? There's a hay bale, there's 2 cars, there's a wall, there's a bunch of stuff. So you have a decision to make about what your system consists of. If it's the part of the problem, I don't remember the problem in detail, but it's the problem I'm remembering where there are 2 cars colliding, and you're asked about something about the final and the initial velocities of the cars, right? Then let's make our system just those 2 cars. And if we also know that there's, like, if the car's not, if neither of the cars hits their brakes or hits the gas while they're driving, right? So, and there's no friction well, let's see, how do we say this? There might be friction forces with the ground. In fact, the cars would be sliding on the ground. They wouldn't be able to turn or do anything if there's no friction. There probably is friction. They have, rubber wheels on the ground that aren't slipping. But if the guy or gal, whoever it is, driving the bumper car doesn't hit the gas or the brakes, and the way the problem is phrased suggests this is a reasonable assumption, you'd say, oh yeah, I'm going to assume it's a closed system and there's no external forces acting, right? So all the forces are just the bumping of the 2 cars. Force of car 1 on car 2, force of car 2 on car 1. If that's the case, then we know that we can just use momentum conservation with, so you'd say final momentum equals initial momentum, and by final initial I mean total of my whole system. Final minus initial equals impulse due to external forces. But the impulse is what? 0, because there's no external forces acting on the cars in that case. So if that's the case, then all right, there's several ways to proceed, right? Remind me, so the question is asking, right, what part are you asking about? About the final velocity? Oh, no, the center of mass. Right. Right. Okay. All right, great. So first you're asked about the velocity of the center of mass, and later you're asked about the individual velocities of the cars. If you're just asked about the velocity of the center of mass at either time, well, what do you know about the velocity of the center of mass before and after in such a collision? Has to be the same. If momentum is conserved, right, in this collision, and there's no external force going on right, for the closed system, so yeah, momentum is conserved and there's no impulse term to worry about for correcting for any external forces, that tells you that P total, or here, let's not do it as a vector, x components of P total, initial, lots of subscripts here, equals P x component total final. So that's the same. What does that mean? It means that the total mass of the system, which is just what? Just the sum of the masses of the 2 cars, times the velocity. Which velocity is this? Equals the total mass times velocity. Final, initial. But what velocity are we talking about here? Center mass. It's got all my subscripts in some random order, stacked all the way to the basement. But just so it's clear what we're talking about. If you find my axis that way, this problem's a one-dimensional problem, as I set it up. You won't be asked any 2D problems tonight, right? Well, you won't be asked any 2D collision problems. I guess there might be 2-dimensional problems. But you know what I'm saying? If there's a collision going on, you'll be able to treat it one-dimensionally. Your job is to recognize what's a collision and use these. Right? So if momentum's conserved, this is true. Well, m is the same. So if m is the same and this equals this, that means velocity center mass before equals velocity center mass later. So what that tells you is, okay, I'm just going to go ahead and calculate the velocity center mass wherever it's easiest. So if the problem tells me the initial velocities of the cars, one thing I could do is calculate the final velocities of the cars, right? And calculate this by saying, oh yeah, what's that equal to? That's going to be equal to m car 1 times v1 final and the extra plus m2. This is totally valid, right? And given that the next part of the problem is going to ask you for these things individually, you might want to do this anyway. But if all you want to know is the velocity of the center of mass, you don't have to go through this and calculate what these things are. You can just calculate it from over here and say, oh, it's just m1 times v1 x, right? Initial plus m2 v2 x initial. And if the problem has one of the 2 cars holding still in the beginning, which may have been the case, I forget the problem in detail, but then one's going to be 0 anyway. So it's going to be really easy. In other words, the total momentum of the system is going to be given by the momentum of just one of the 2 cars in the beginning. No one's moving. And then all it comes down to is the ratio of the masses, right? Because the thing is, the velocity of the car that's moving in the beginning is not the velocity of the center mass, right? Because both cars have non-zero mass. But it's easy to calculate because all you have to do is, you're given that velocity, you'd say, okay, well, if this is m times v sub x center mass, that means that v sub x initial center mass, what does that equal? It equals all this divided by capital M. And if this is 0, if this guy had no velocities, oh, it's just m1 over total m of v1, right? I think I did that right. Initial x. Yeah. So in general, when you've got collisions and you know momentum's conserved, that means and there's no external forces acting, right? So I mean really conserved, not just conserved plus a correction term due to impulse. Then you can just find the place that's easiest to calculate what the center mass is doing, and it's going to keep doing the same thing to the whole problem. And that's true even if you've got 3 objects in the mix, right? There's a problem like there's that winter cannon problem, there's a cannon, there's a cannonball, there's a target, there's all these things. But until that cannonball, until the cannon itself bumps up against that spring, right, in that problem, that's when you get external forces from, because that's connected to the Earth, right? So now, okay, you make a system that includes the Earth, but then it's tricky to use these laws because you don't know the velocity of the Earth is so close to 0, it's unmeasurable, and it's not given in the problem description, it's hard to work with. The mass of the Earth is so giant compared to masses of the objects in the problem. So before that cannon hits the spring, you can just treat it all like, okay, center mass motion doesn't change of my system, consisting of the cannon, the ball, the target, right? And in the beginning, what's going on? What's moving in the very beginning of that problem? Do you remember? Well, before the cannon fires, what's moving? Nothing. So what's the velocity of the center of mass in that problem? 0. Through several collisions, it stays 0. So if you're asked, okay, what's the velocity of the center of mass later in that problem, after the ball shot and the ball hits the target, and the center mass of what? Of the target plus the ball plus the cannon? 0, right? Because momentum's conserved. And up to that stage, there's been no external force on your system consisting of those 3 things. So that's, so when it comes to center mass, several students come to and said, well, why do you convert things to the center mass coordinate system? Why do you do that? You don't have to if you don't want to. If I ask you what the velocity of the center mass is, please answer that. You got to answer that. But you don't have to solve problems by converting to the center mass coordinate system. But if it helps you think about it, it helps me think about it. It's easier to get things right for me to do that. But there's more algebraic steps when you do it. So it's just a matter of how you want to think about it. But anyway, okay, so does that address the... Oh, right. Then you ask the second part. Right. Yeah. Oh, yeah, that's exactly what I just meant. Yeah, so you're asking the thing I just mentioned, which is, okay, when you go to the next stage, suppose, okay, so that we just talked about center of mass velocity, but what if they ask you, right, to solve for these things individually? There's several ways you can do that. mean, there's sort of three ways in my mind to go about doing that. One way to do it is to write down explicitly, well, let's see, kinetic energy is conserved. You write it all out, right? 1 half m1 v1 squared plus for 2 equals, right, for the other two guys, final. And then write down the second equation, momentum conserved, m1 v1 plus m2 v2, and so on, right? And if you have both those equations, and you're trying to solve for two final velocities, v1 final, v2 final, you're golden, right? You got enough equations and enough unknowns, but it's kind of a pain if you go through it. The grader knows what you're doing, totally understand that you know both these things are conserved, you know, you're doing great, right? You get through it and you solve it. That's one way to solve it. Another way to solve it is to skip to that equation that's in the book and probably on your sheet, probably on the test, that incorporates those two things together. So there's an equation that says v1 final equals, and then there's two things added together that are both complicated fractions of, like, that's what you get if you go through the algebra, starting with conservation of momentum, conservation of kinetic energy. That's a perfectly valid way to solve the problem, but make sure it's valid and tell the grader you know what you're doing. Explain, you know, say, well, it's an elastic collision, kinetic energy is conserved, momentum is conserved, therefore I can use this equation, which is valid under those circumstances, and you only have two objects that are colliding, right? That's what that equation's for. If you don't explain why you're using it and why it's legitimate just to jump to that equation, and then you make some error, which is really easy to do when you're going to test and you got things out or whatever, then you don't get as much partial credit out of it. Like the grader's not sure, well, maybe they just copied the equation that's got a v in it and don't really know what they're doing. If you explain what you're doing, it's easier to get partial credit, and it's all about partial credit on a physics exam in any class, including this one. So what you want to do is justify why you're using the equation you're using. Tell them it's an elastic collision, right? If you choose to use that, and it's such a thing that occurs on tonight's exam. I forget exactly what's on there. What else? Oh yeah. So then I guess I said there's a third way to solve it. Is that true? I'm sure there's 20 ways to solve it. Yeah, the way I would do it is by starting writing down conservation of kinetic energy and then doing algebra and arriving at that expression that's in the book and then solving it. And then okay, that's the whole deal. Then the second way is just to skip to the chase with the justification in words of why you can use it, use that formula, and be really careful to use it properly, and be really careful that you're putting in the right velocities and masses in the right places, and check your answer that it makes sense, right? I'm trying to think if there's a third. I told you there were three. There is a third sort of standard way. Yes. Thank you very much. Yes, that's right. So the third way is one of those ways, but it's sort of, but right, it's where you convert to the center mass coordinate system, and the equations are so simple in that reference frame, it doesn't feel like you're doing the same thing, even though that's what you're doing. So that's right, and that's what you're asking. So what you do is you say, okay, my initial situation, I've got a moving guy and this guy that's holding still. Let's convert to the center mass coordinate system. So what does that look like? It looks like this. I'm moving my head along with the center of mass, right? Say, oh, well, this guy's holding still with respect to the laboratory frame, or in that case, whatever it is, the racetrack, or the, I don't know, the pond, or whatever the situation is. But this thing that's coming in now, if I move my head halfway between, if they're equal mass, if I'm halfway between, then I see him coming this way and I see this guy coming that way. They're coming together. And then afterward, when they bounce off, well, if it's an elastic collision, all I do is change the signs of those velocities in the center mass coordinate system. So how do you convert things to center mass coordinate system? And what do you do if the masses aren't the same? Sort of obvious. They're in the middle if they're the same. If they're not the same, then you figure out the velocity of the center of mass using what you say, what is the velocity of the center of mass? You say the velocity of the center of mass equals velocity 1 m1 plus velocity 2 m2 all over m1 plus m2. It's just a weighted velocity. That's one way to calculate. That's how you calculate explicitly the center of mass velocity, right? And then once you've got that, you subtract this quantity, if you'd like to do the problem this way, from all the velocities in the problem, before and after. So you have four velocities, v1, v2 initial, v1, v2 final. You subtract that quantity from all of them, all the ones you know. And then you've got a situation where initially what's happening is the center mass has velocity 0 in the center mass coordinate system. In comes velocity, one guy's going this way, the other guy's going the other way. If let's say this is v1. If v1 is more massive, then is he going to be moving faster or slower than v2 as seen in the center mass coordinate system? Slower, that's right. The more massive one must be moving slower because in the center mass coordinate system you have back-to-back momenta, equal and opposite momenta. The only way that's possible if you have different masses is if they have inverse velocities to their masses, right? If the more massive guy's going slower, the lighter guy's going faster. And then after the collision, what happens? If it's elastic, you just change the signs on all the velocities. If this guy came in at v1, he's going out at, or v1 prime for center mass coordinate system, he's going out at minus v1 prime. Right? And same thing for v2. And then what you have to do is convert back to the laboratory frame, or the original frame, so you can answer the question in the frame that you were given the numbers in the first place. And say how fast is v1 and v1 and v2 moving? You just add back on the center mass velocity to each of the velocities you get for v1 and v2. So if you do it that way, it's true that it's a different operation algebraically. You don't have to go through all those equations for kinetic energy and momentum and all that stuff once you put yourself in the center mass coordinate system. At least for two cases. And the two cases are, well, I'd say three cases, but you have all the information you need for two cases. One is maximally inelastic collision. So in the center mass coordinate system, if two things come together and they bang together and they stick together in maximally inelastic collision, what is the final velocity going to be of each of the guys after the collision as seen in the center mass coordinate system? I think somebody said it, but most of you did. 0. If two things stick together, then the center mass is right where they are. If you're viewing it from the center mass coordinate system, the center mass is holding still, right? So they're holding still. So if you have this situation, equal masses, this guy's moving, he's not, but I'm moving up the center mass. Now they stick together, and I'm moving right with them, right? So from my perspective, velocities are 0, and then when I'm done, all I have to do is say, oh yeah, then their final velocities are each going to be the velocity of the center of mass that I calculated in the beginning of the problem. So if it's maximally inelastic, and you have two things colliding together, once you know the velocity of the center of mass, that's going to be the final velocities of all the objects. If it's elastic, then they bounce off, you just change the sign, convert back. Anyway, so those three ways all work fine. They're all totally valid. Don't ball them up and do one and the other. Make sure you do something that's self-consistent. Yeah. So if you try to solve, so the question is, how do you know that it's valid just to change the sign of each of these? Why does that work? You can see that it works because clearly momentum is conserved. Momentum initially is 0. Momentum at the end is 0. There's a back-to-back momentum in, back-to-back momentum out, and you're done. You just change the sign on these things. If this plus this equals 0, then change the sign on each of them. That's negative 0 is still 0. So good, momentum's conserved. Kinetic energy is conserved because 1 half mv1 squared equals 1 half m times negative v squared, the negative square. So the kinetic energy of each object is preserved, so therefore the kinetic energy of the sum of kinetic energies is conserved. So you see right away that it satisfies conservation of momentum and conservation of kinetic energy. It must be a valid solution. There are only two valid solutions you get. Because of that square in kinetic energy, you get two valid solutions when you solve the equations. What's the other one? The other one is when they miss each other. So one way you can conserve kinetic energy and momentum in a one-dimensional collision with two objects is if they pass each other by. That satisfies conservation of momentum. Each of their individual momenta don't change. And the kinetic energy is conserved because each of their kinetic energies don't change. So that works. If they bounce off each other, as seen from the center of mass coordinate system, the only way to get the numbers to work out is if you wind up going, you give the same speeds to each object. But if it's one dimension, there's only two ways to get a certain speed. Either it's going to the left or to the right. So you just change the sign. So that's sort of just thinking through. Like we could do the algebra. It's a little tedious, but that's the result. There's only two ways to satisfy both conservation of energy and conservation of momentum with two colliding objects in one dimension. And that is if they pass each other by, or if, as seen in the center mass coordinate system, they bounce off and just change the signs on the two velocities. Yeah. So if you don't subtract the center mass velocity, and that's perfectly fine. But then you can't just change signs of things and have the answer. You have to calculate what velocities you need, as seen in the laboratory frame or whatever it is, in order to conserve energy, kinetic energy, and momentum. It wouldn't. If you change the signs on things, you get the wrong answer, right? So in other words, there's 3 ways I described to solve it. All those are valid, but you can't take the easy parts of the 3 ways and put them together and avoid the doing the calculation part. Right? You'll get crazy answers, if that makes sense. Anything else? Yeah. Okay, so you're talking about the problem is the ball that hits the target. The target is still, the ball is moving, and then after the fact, and they're equal mass. So that means that, so you know what's going to happen. So first of all, the rubber ball and a wooden target, is it elastic or inelastic? It's a good approximation to say it's elastic. And you'd say, yeah, it's a rubber ball, it's probably an elastic collision. It's not a piece of clay or something, right? Or it's not a nail or a bullet or something that's going to lodge itself, right? So good. So what's going to happen? If this thing comes in at some, you're saying you weren't given the initial velocity of the ball? Oh, I see. Well, yeah, so it's true. If I don't give you enough information, you can't solve it. Or it got lopped off in the Xerox or something. I don't know. I don't see what I have. I apologize if there's missing information. So the thing is, I don't remember off the top of my head how that specific problem, but clearly what I intended for you to do is to come up with, is to have been given or been calculated from some previous part of the problem or something, that initial velocity. You need to know, you would need to know the initial velocity of the ball, as you surmise, to be able to figure out what the final velocities are. It might be there's some other way to find it out, though, other than being told. But based on what you're telling me, it sounds like it was just omitted, like it was an error and it was written on the board during the exam. That's possible. Although I should have gone back and corrected that, I'm surprised. Sorry? If it's on the answer key right off the bat without explanation where it came from, that's probably what it was. Yeah. That's right. If the ball, and you've seen this over and over. If you're in a frame where one gets still and one's moving and there's an elastic collision, you know what happens? The one that's moving winds up stopping, the other one has to move. Now, in order to get full credit, especially if there's anything dubious about any other part of your problem, right? You want to convince the grader what you're doing. You want to tell them where that comes from. Say it's an elastic collision, kinetic energy is conserved, momentum is conserved, and there's only 2 ways to achieve that. Either the thing misses the target, and the ball moves at the same velocity before, and the target stays at 0, or they bounce off each other. This guy moves away at the initial velocity of the ball, and he holds still. If they're equal mass, they either have to exchange their velocities or keep them the same as they had in the beginning. It's the only way to conserve kinetic energy and momentum in 1D for 2 objects. Yeah. Anything else? Yeah. So I won't test you on that. I won't test you on billiard ball problems where there's 2 balls that come in and they bounce, or air hockey where they do this. Or actually, air hockey only has 1 puck, but where you have 2 things come in and they bounce like that. I won't test you on it. But if you're interested in how to solve it, I'm thrilled to show you how to solve it. Come off hours when we go through it. But the way you solve it is with you just conservation of momentum in 2 different dimensions. And then when you do that, you wind up with a simple formula that involves the angle of the deflecting. You get the angle of that they go out, theta, whatever, as a function of how far off center. The issue is how far off center they are, right, in terms of their trajectory, the center mass trajectories of the 2, and also their diameters, right? Yeah.
You did an example in lecture, beginning of the unit on elephants in a train.
Elephant in a train, yeah, right.
Yeah. The center of mass stayed the same.
Yes.
The center of the train moved, and you want to calculate how far the train moved.
Yeah. So if you're going to a problem like that, if you have a problem where, again, this is all center mass stuff. If you have a train car with an elephant inside or something like that, and the elephant moves over some distance, the train goes the other way, you know, given the fact that the initial center mass is holding still, that after the elephant does his walking, if there's no external force, if there's no rusty wheels on the train, and there's no force being exerted sideways, horizontally on the train or the elephant from external forces, then once the elephant stops walking, the centers of mass of those 2 objects will have moved over and stops and be holding still at the end, and the amount they moved over is inversely proportional to their masses, right? So if the train car is twice as massive as the elephant, the train car is going to move half as far as the elephant moved, because the center of mass never moved of the system consisting of the 2, right? And so if one's more massive, it goes less far, right, compared to the other. But does that make sense? And so we can calculate it explicitly. If there's a fact, yes. So if the mass of the elephant is half as much as the mass of the train car, then if the train car moves over 1 meter, the elephant moves over 2 meters in the opposite direction. Because when you calculate center of mass, when you say, x center of mass equals mass 1 times x1 plus mass 2 times x2 over m1 plus m2, it's just a mass weighted, it's just the average location of those 2 things, right? You can put an initial, and that has to equal final, same equation with final, right? The only way to make that true is if this winds up, if you wind up having some, you can make these delta x's, that make just have one single formula. The amount of displacement this guy has from, let's say that 0 is the initial center of mass of, let's say they both have the same center of mass initially, just to make it easy, but it doesn't matter. It doesn't matter if they did or not. If you say how far is the center of mass, well, we know this thing doesn't move, it's always the same value. So to make this thing the same, whatever this does in the positive direction, that's got to do in the negative direction. That's what I'm saying. And so if this is twice as big as that, that's twice as big as that. If those are delta x, how far x has moved. Yeah. Yep. Yeah, okay, so let's talk a little bit about torque. So the question is, why does a string on a yo-yo do no work? Well, let me ask you this. Why does a wheel rolling, so if a wheel rolls down a ramp, yeah, I'm surprised there's no torque questions so far. Anyway, so if you got a wheel on a ramp, when that wheel rolls down the ramp, how much work does the ramp do on the wheel? If it's rolling without slipping, I mean, just to be really clear. So this thing's rolling without slipping down the slope. What is the free body diagram for this wheel? How many forces are acting? I'll do an extended sort of free body diagram where I can see the whole thing and draw all the forces. How many forces are acting on the wheel? 3, right. There's gravity. Where's that gravity act? Center mass. Let's say it's a wheel that's evenly distributed mass. Okay.